Okay, we study X22Q properties of waves. So you can download this PDF file by visiting our library, digital library, kpop.org, and we are working on X series, and there is X22. The main textbook is X, and if you click this, you can watch a lecture
이번
in Korean.
시간에는 파동
And if you click this, you can
in this
watch
class
English version.
we study property.
And if you click this, you can return to our digital library. Okay. And you click X22C. There are multiple choice problems asking a false statement, but even if it's asking a false statement, that there is no, that everything is correct if there is no typographic mistake. So if you find any typographic errors, please let me know. Now we study X22Q. Okay, after completing this lecture, I will upload the file, the video file at the YouTube, and Korean version is, oh, wait a second, it's not connected yet. So if I finish this, let me upload to YouTube. And our YouTube site is here. So youtube.com at KPOP. Okay, you can visit here to click the playlist, and there are many kinds of lectures available. All right, X22Q properties of waves. Okay, explain how to use Euler's formula to derive the addition formulas of the trigonometric functions. Okay, we first make use of complex number. Complex number is a linear combination of unity and what's that? This is a pure imaginary number I defined by square root of -1. And the coefficient are called the real part and imaginary part. And we can name them, the real part to be x and the imaginary part to be y, that correspond to the Cartesian coordinate in the two-dimensional Euclidean space. So complex number for real and imaginary part, and a point, a complex number, and a point in the two-dimensional Euclidean space expressed in terms of Cartesian coordinates, they have a one-to-one correspondence. Okay, so that's the reason why we can introduce the magnitude of complex number that is the same as the radius from the origin of a point expressed in terms of a Cartesian coordinates. So that is a square root of x squared plus y squared. In addition, we can introduce an angle, alpha, polar angle, in the two-dimensional polar coordinate system. representing the two-dimensional Euclidean space, then the x-coordinate should be the r, if I write it as a radius r, then r cosine and r sine to be the x and y, respectively. Therefore, if we make use of these facts, then z is x plus iy, and x is actually r cosine, and the y is r sine, so this. So we can define this one by e to the I alpha. However, we could either define this or prove if it is really true. Exponential I alpha is identical to cosine alpha plus I sine alpha. That is called Euler's formula. The Euler's formula can be obtained directly from the Bernoulli definition of Euler's number. That is this. And if you apply, we already have studied it frequently. So we apply the binomial theorem to reproduce the expansion of this. K runs from 0 to infinity, 1 over k factorial. In addition, if you attach a power to this identity, we have exponential x. And this one is a limit as n goes to infinity, 1 over n and nx. Why don't we redefine nx by nx and nx? Or for example, for the positive x case, then we redefine this by n prime. Still, it runs not an integer anymore. However, it goes to approaches infinity. In this manner, I can express this one to be this and apply the binomial theorem again and kill all of the finite k-dependent term divided by n. As n goes to infinity, then this guy will all killed. Therefore, this one can be expressed as a power series in x. If you refer to the previous versions of the smaller number x, then you will find that this is true for any real number x. Okay, so in fact, we have I has a square root of -1, so therefore I squared is straightforwardly obtained as -1. And again, if you take the even power of I, then it becomes -1 the kth power. So it is flipping its sign. When k equals to 0, it is 1, but after that, it oscillates +1, -1, and so on. In a similar manner, if I take the odd number of powers of I, then this rule can be applied to find that it is proportional to the pure imaginary number I with an additional oscillating factor. As a result, we extend this one to a complex plane, especially along a pure imaginary number. This is called the analytic continuation. And analytic means it is a continuous, a differentiable, something like that, in complex space. So this algebraic approach allows us to find the power series expansion, even if I include the argument of a complex number. Then finally, we arrive at a point that we have I. Wait a second. This is wrong. this minus k must be removed. Wait a second, let me correct this. Okay, I have corrected the negative. This one was wrong in the previous version. So I alpha is kth power divided by k factorial. I split this sum into two pieces for even numbers and odd numbers. If I have even numbers, I to the 2k, this one replaces the even power of I as an oscillating factor. In here, this one is applied here to express, I factor this pure imaginary number I out to find that is cosine plus I sine. We can apply the additive law of power exponent, and this one can also be derived using Bernoulli definition. For example, these two factors may have different powers. Suppose that we have n greater than n prime. Once we obtain this result is also working in opposite case or identical case. We can separate it into two pieces, the same power and the difference. Because n is assumed to be greater than n prime, we have additional factors of 1 plus z over n. Okay, however, we assume that the difference is finite and we take the limit as n goes to infinity. So this is a trivial unity. In addition, this part, if I apply the binomial theorem, any higher order piece of order n squared or higher, they completely disappears. And therefore, we don't have to consider this and only the 1 plus 1 over n style. It is apparent that the additive law of exponent is valid. As a result, we can multiply two complex number with unit modulus in this kind of form, and that z equals cosine alpha plus I sine alpha. Applying the additive law of exponents and substituting the expression, where is it? Cosine plus I sine. And find out the real part and imaginary part. Because any complex number is identical to another one as long as, and if and only if, both the real part and imaginary part are the same, respectively. Therefore, this method applies here. Product of two unit modulus complex number can be expressed as a product of Euler's formula with depending on these two parameters, alpha and beta. We could expand this. The real part is the product of real part and minus the product of the imaginary part. And the imaginary part of this product is the real imaginary because I appears only once. As a result, we can find the real part to be cos minus sine. And the imaginary part is cosine sine cosine. However, we remember that this guy is the same as this guy, a single unit modulus that is exponential alpha plus beta because of the law of exponent. Therefore, the real part is cosine alpha plus beta, and imaginary part is sine alpha plus beta. Finally, we can reproduce the addition formulas for the trigonometric functions. You can reproduce this result by copying this to Mathematica. Next, we consider what is the beat frequency of the two sound waves. A beat frequency, okay, we have two waves, and we remove the spatial part and we just consider time-dependent part. And for simplicity, we have chosen the two waves initially they were the same. I mean, they don't phase difference at all. The only difference is the period and all this angular frequency. Angular frequencies can always be scaled by 2 pi. That is the period of a sinusoidal function. In that case, then it's better to find out 2 pi multiplied by frequency. That is just the reciprocal of the period. We assume that these two frequencies are very close to each other. We can say f1 and f2 to frequencies as a simple algebra will tell you that it is the sum of the average of these two and plus something or minus something, where the something is 1/2 of the difference. Any real number, any vector, we can do this job. All right, in that case, we can make use of the addition formula. We know this by substituting this one to be alpha plus beta and this one to be alpha minus beta. If you have cosine alpha plus beta, you have this. If you have cosine minus alpha minus beta, you have plus. And same thing. If you add them up, then this cancel and you have a factor of 2 of cosine cosine. And therefore, the answer is a factor of 2, amplitude common amplitude A and cosine cosine, where alpha and beta are given in here. I just copied the result in there. By the way, we know that F1, F2, and 1/2 of F1 plus F2, the average value, all of them are very similar to among each other. Therefore, we factor this out. An additional factor of cosine will give you this. If you look at this frequency is similar to the previous one, original two frequencies. However, this frequency there is a great cancellation, so this frequency is small. The frequency is a small frequency means a longer period. So the original sound wave in the time space, they are quite close to each other. However, this guy, we say it is envelope is growing up and down, up and down, up and down, but very slowly. So that is a beating. This is beat. Okay. So you will notice that bead has in a single envelope created by this, and the period, what is the period of this vector? This is the period. However, we don't really know the difference between this part and this part. Our eye is not is not is our human ears are not machine. We cannot distinguish these two parts because mostly we do not measure the phase. There are difference in phase of the two parts. However, our ear just understand, distinguish the change in the magnitude that is called intensity. Therefore, the frequency of the envelope that is related to this is double. What I mean is this I do not distinguish, so a single period is sliced into two periods. So we have a shorter period and factor shorter period one by one half. That frequency is doubled. So frequency is doubled. So beat frequency is how many times you have this envelope in unit time. That is the beat frequency. And we have to multiply factor of 2. Even mathematicians are at the ear. Mathematicians are human, and the physicists are human, students are human. Human being does not distinguish this and this. Therefore, we have to multiply factor of 2. That is a beat frequency, and that is the absolute value of the difference of the two original frequencies. Number 3, consider the propagation of sound waves in a steady state along a cylinder of cross-sectional area A and height L. Cross-sectional area A and height L and volume V. The current density, let's assume that x plus L, and we will replace this L by a tiny piece that is called delta x. Okay. F may be a pressure, density, velocity. By the way, we do not have time dependence in it. No time dependence, because we assume that this state is independent of time. That is called a steady state. A steady state means our distribution of a pressure, velocity of the oscillating molecules due to the sound wave, they are independent of time. So steady state. All right. So because we consider this steady state, we suppress the time dependence and consider x dependence only. Okay. And the width is now width, this height. Okay. So the height is L is replaced with a tiny one. That is called the differential delta x. So we replace this one with the delta V, and we consider the mass inside this part to be delta M. What is the mass? Mass is the density times a volume. And this volume is density, cross-sectional area, and width. That is delta x. That's fine. And then we identify this position vector x to be x, real number E1 hat. And this point, that is x plus delta x vector, something like that. Okay, we consider the net force applied to these molecules contained inside a tiny volume. The force can be computed by making use of the pressure. Pressure multiplied by the cross-sectional area. Because we are considering very simple structure, that is a cylinder, and this axis is the cross-sectional area is fixed to be constant. and it is this area is perpendicular to the length. We have a pressure on the left that's pressing this molecule, this set of molecules to the right, and another pressure is pressing this to the left. Therefore, we have at position x and x plus the delta x, pressure multiplied by area is the force, and the unit vector represents the direction of this force. What about the right-hand side? That is the same pressure but measured at x plus delta x. And cross-sectional area A, and then unit vector that is minus E1 hat, because it is this pressure is applying force from the right to the left. As a result, if the delta x are very small, then we can expand this. We have this the difference of the two pressures at x and x plus the delta x. This delta P represents the difference between P x plus delta x, the bigger the right side, subtracted by the left hand side. Okay, this one can also be expressed as a product of this total differential in powers of differential of x, because of the time independence of this steady state solution. We can just take the partial derivative with respect to x and multiply the differential of x. All right, so we remember that delta M is contained inside this tiny volume, and volume is a cross-sectional area multiplied the thickness. Therefore, the mass is the rho delta V, rho A delta X. So that's fine. We apply the Newton's second law to find out the net force in a different way. Newton's second law states that the net force applied to a system of particles is a mass of total mass multiplied by the acceleration. So we have mass times acceleration structure. Previously, we have obtained that the net force can be computed by the difference of this pressure on the left and right and left. And we substitute this result. By the way, what we have found in here is, because of the cross-sectional area is multiplied by the thickness, we have reproduced a volume in it. Okay, do we have volume? Or why don't we find the mass by making use of volume? Then I have to multiply the density. But if I multiply the density, the value differs from this, so I have to divide it by rho again. So what I have done is multiplied by 1, and 1 is a rho over rho. Simple. And then rho multiplied by the volume is the mass. All right, so I eventually have found that these two masses cancel exactly, so mass dependence cancel. So I have found the simplified version. Acceleration is just net force divided by mass. That is a negative 1 over rho, and this derivative. All right, in here, we can compute acceleration by changing the velocity part. Okay, so we do not have time dependence, so this evaluation can be made by substituting x plus the right hand side, so right hand and the left hand subtraction. So evaluated on the right side and left side. And here, this x dot is the velocity v. All right, so because the acceleration is the time derivative of velocity. So this the change in the velocity on the right side and left side. That is this. What we have found previously is the acceleration is this, and substitute. And then what happens? What happens? What happens? What happens? Rho, the same. This guy, the same. But we have delta t. Delta t is the delta x is a v delta t. Therefore, it is replaced with delta x over v. Therefore, the x cancels to reach the point, the change in velocity. This was a scalar velocity, so the vector velocity is multiplied by the unit vector along that direction, this E1 hat direction. As a result, I can substitute this one in here. This is a carbon copy of this, and this is copied to here. Finally, we can remove the parallel unit vectors to find that the change in velocity on the right side and left side plus pressure divided by density velocity, that is 0. So let us simplify this. If we can multiply this factor, rho v, what's that? Current density, rho v, current density. Okay, we multiply this factor, both sides. This one doesn't change, and we have pressure change, and the density, velocity, and change in velocity. So this one appears in here. We have v delta v, that is 1/2 v squared differential. You know this. All right. We applied the steady state condition. This one must not have time dependence. The continuity equation of mass flow states that the right-hand side vanishes. In that case, divergence J is a 0. Divergence J is a 0. Then we integrate over volume of delta V, and you will find divergence theorem states that this is a J dot d sigma, and this one is still 0, and this is over a closed surface, but this side of pipe does not allow any mass transfer. Only here current flows in, here current flows out. Therefore, what we have is this flow and normal vector of the surface are opposite. So evaluated at x has negative sign in the flux vector, flux contribution. On the right side, evaluated x plus delta x, we have a parallel component of the normal vector of the surface and the current. Therefore, this is a plus. If you simplify the whole expression, what I find is the current density is invariant because the cross-sectional area is fixed to be constant. As a result, this current density conservation states that change in this must vanish, but this current density is a product of density and velocity. The differential is using Leibniz rule. All right, because the sum is 0, we have this condition. rho delta V and V delta rho, they are the same in magnitude but opposite in direction. We make use of this the consequence of the continuity equation into the result we obtained previously, coming from the Newton's second law. So Newton's second law is used to substitute this. Finally, you have delta P equals, if I migrate to this one to the right hand side, this, and what about this? This is this. I have replaced the sign, flipped the sign, but exchanged the delta from V to rho. Minus minus plus, we have velocity squared and then delta rho. This identity results in the fact the speed. This is a scalar square. The speed is a square root of a pressure, square root of pressure over density change. This one shows that pressure increases as density increases. They are parallel. The steady state condition can be used to find additional. This one was already used, but in reverse, we can also, well, one more time we can use. From this, move, divide rho v. Okay, so we obtain this. Why don't we multiply 1, that is a cross-sectional area multiplied by time difference? And then cross-sectional area multiplied by time dependence. Cross-sectional area multiplied by time dependence, multiplied by V. We used the fact that delta x is a V, delta x is a V delta t. This is the speed of sound. That means the speed of the transmitting in this information. As a result, this one can be replaced with the width delta x, a delta x. What's that? A delta x. That is a volume. Cross-sectional area and delta x, a volume. And we have another differential in here that represents the pressure change will compress this volume with a tiny amount. You know, the membrane of a speaker vibrates. This vibration results in the change in volume of this gas. That is related to speed of sound. Okay. Finally, this one is this. Okay. So delta rho can be replaced with minus rho delta V over V. The appearance of negative sign is that if you have increased density up, then pressure is up. If the pressure is up, then volume is down. So because of the correlation of the density, pressure, and volume, we have negative sign on it. So originally we have obtained the speed of sound as a square root of pressure density differential ratio. It can also be expressed in terms of pressure volume change per whole volume. divided by density with a negative sign. The sign comes from this correlation among density, pressure, and volume. Finally, we define this one by bulk modulus of this gas or liquid divided by density. We recall that the propagation of wave in a tight string vibration, it was the tension divided by rho. Just like the tension in the vibrating string, the gas molecules inside the cylinder behaves as a tightened string, and that is parameterized by the bulk modulus of B, just like tension. Okay, by the way, this rho is the mass per unit volume, and in the string case, this is a mass per unit length. That's it for today. Thank you.